Hello students, today we will discuss about electric field due to continuous charge distributions. Electric field of continuous charge distribution. We have seen how to find net electric field by point charges. If there are multiple charges, we add them in vectors. So by using the same principle, we will calculate the electric field due to continuous charge distributions. Continuous charge distribution means an arrangement of an array of charges. For example, I have arranged some positive charges along a line, right? This system is an arrangement of series of positive charges, very closely spaced. Or you can take an insulating rod, you can charge it. An insulator rod, when charged uniformly charged insulator rod. So when it is charged uniformly, that means the charge is present uniformly on the substance. Here in the case, it is a rod. So the charge will be residing on the rod uniformly. Such systems are called continuous charge distributions. So in such cases, we generally use these kind of terms. Lambda we use for charge per unit length. Generally we use this. For example, if you have a disk, right? Insulator disk. Now if it is uniformly charged, that means the charge is present on the disk uniformly. The density is same everywhere. So it is uniformly charged, whether it is given positive charges or negative charges. If it is uniform, in such cases we use this term sigma. This is charge per unit area. So what do you understand from this? So if the length of the rod is L and the total charge on it is Q, it has Q charge given to it, then lambda is equal to charge per unit length, Q by L. This is what we understand. Similarly here it is charge per unit area. So if this disk has a radius R, its area is pi r square. So sigma is, if it is given Q charge as well, the total charge is Q, sigma is Q by 4 pi r square. These are the terms we commonly use. Similarly, we use rho for volume distributions. For example, there is a solid sphere, right? The charge is present everywhere within the solid sphere. Uniformly everywhere throughout the volume of the sphere. That means it is a distribution of charge in volume. You have a 3D space of uh, complete positive charges. So this is volume distribution. This is areal distribution. This is linear distribution. So in such case, we use this term rho. This is charge per unit volume. So if the total charge given here is Q, the Q charge is present within the volume. It is present everywhere inside. So rho is Q by per unit volume, right? So volume of the sphere is 4 by 3 pi r cube. So this is what you understand from this. So these are the terms we commonly use in the following lecture. So our first case, electric field due to a arc. That means we have a charge distribution, but it is a portion of the circle, right? The shape is an arc. So it is the portion of a circle, it has its own center. Let that be O. So we have to calculate the field at the center. Field at center. So what could be the field at center? How do we approach it? So the idea is same thing. We apply superposition. So this is what we do. Whenever there are multiple charges, here also there are several charges. So we have to calculate the field at some point due to all charges and add them vectorially. This is what we have to do. But since this is a continuous charge distribution, now we have integration approach for this. We can't add one by one. We will integrate. Let's see how we do that. So the field at O, we have to first understand the system carefully. So let's draw it bigger. Let us say this arc is subtending an angle alpha, right? So at O, let us take a small portion of the charge distribution. It is also a linear charge distribution, but the line is curved, an arc. So if it is given a charge Q and it has a length L, then Q by L is lambda. L is length of arc, right? So let us say it has got a lambda, charge per unit length, we know that. So now if you take a small portion of dl length, it has dl length. Now dl can be calculated using the length of arc formula. We have taken a small portion, let us say it is at an angle theta, measured from the bisector. We have taken the arc symmetrically. So along the x-axis, we take the bisector of the arc here. It is a simple way to do this. So let us place the arc in such a way that the x-axis is the bisector, and the theta angle is the angle measured from the bisector. To which location? A certain location which we have taken here, the small portion. We are considering the small portion. Its length is now r d theta. If this small angle is d theta, right? Length of the arc, r into angle. So this has a length dl. Now what is the charge present on it? dq, the small charge present in this portion, right? We have small charge dq here. Capital Q is the charge distributed on the arc, total arc. But if you take a small portion, there is only some charge present, elemental charge. So this dq is elemental charge. So its value will be charge per unit length lambda into the length itself, which is dl, that is r d theta. So now we'll calculate the field due to this elemental charge at O, and we'll try to integrate it. So before going into integration, let us think about the problem. What will be the field at O? How is it oriented? So due to this, you will know that there is a field, small field due to the small elemental charge dE in the same direction. From the charge, the field is going outwards. So in this particular direction, at this point, the field is going in this direction, dE, the small value of electric field. It is acting along the same line. Now, if you carefully observe, there is an identical elemental charge on the opposite side, right? For which the field will be of same value dE in this direction, right? So if due to this charge there is a field in this particular direction, by symmetry we know that a charge here will cause the field in this particular direction, and the value will be same because the distance is same, right? Now compare these two vectors. For these two vectors, if you resolve them into components, there is one dE and its vertical component, horizontal component, another dE. So there is a vertical component and there is a horizontal component. So this field is seen as sum of these two components. This field is seen as sum of these two components. So this is dy and dy. This is dx and dx for this. Now if you look at this scenario, the vertical components are opposite in the directions, right? One vertical component is downwards, the other vertical component is upwards. So if you take any two symmetric locations, whether here or here or here or here, symmetric locations at the same angle above and below, now the field produced by those two will be in such a way that their vertical components cancel out. So as a whole, if you see the field produced by this and the vertical component of all of them will be cancelled by the field produced by this and their vertical components. So the vertical components cancel off. What will be the result is we will be only left with the horizontal components, right? So all vertical components cancel off. This is an important step. All vertical components cancel out. So we have taken the figure our system in such a way that we have a simple method. Now by taking it along the angular bisector, the advantage is that we can reduce the problem, the way it is less complex. We have arranged it in such a way that the vertical components are cancelled out, so our problem becomes easy. All we need to do is now calculate the field due to horizontal components and add them. So what is the horizontal component? dx. What is dx? So if this angle is theta, this angle is also theta, right? So dE cos theta is the horizontal component. Now what do we need to do is to calculate the total field, we have to integrate this. So Ex is integral dEx with proper limits. So let us do this. dE. Now what is the field produced by elemental charge? How do you calculate the field due to elemental charge? It is an elemental charge. That means it is a point charge, very small. So for point charges, we know how to calculate the field. So dE is kq by r square. So k into q is the small charge. So it is lambda r d theta, kq by r square, the distance. Distance is the radius itself. So we'll substitute that here. It is 1 r goes of lambda k, let's write k in front, k lambda d theta by r cos theta. Now we have to integrate this from which portion to which portion, what are the limits. Now theta is measured from the bisector. See, it is measured in anti-clockwise sense. Now for integration, we always integrated any expression considering that the integration variable, right? In this case, the integration variable is d theta, right? We have d theta, so theta is our integration variable. Now theta should be varied, the limits should be given in such a way that the theta is from lowest to highest, right? The lowest value of integration variable to highest value of integration variable. This is how integration is done. So in this case, if you want to include all the charges here, how should you vary the angle? What is the lowest angle possible? Is it 0 degrees? If it is 0 degrees, the point is this, right? Theta becomes 0 and we are considering this point. If it is alpha by 2, see, the whole angle is alpha, so this is alpha by 2 and this is alpha by 2, right? Alpha by 2, alpha by 2. Now if you vary from 0 to alpha by 2, you will involve only these charges. These will be neglected, but that is not what we should do. We have to include all the charges. So you have to vary theta from this portion to this portion. So you have to consider all the elemental charges in that region. So how do you vary the angle? Right. So from the reference line, this is reference line. Remember, from the reference line, you have to properly take the angles. This angle is measured as minus alpha by 2. It is clockwise. And this angle is measured as alpha by 2, positive. Right. So theta, if it is above, it is positive. If it is below, it is negative. Right. So in this case, we have to vary the angle from minus alpha by 2 below the x-axis, minus alpha by 2 to plus alpha by 2. These are our limits. Now let us do this. K lambda by r are constants. You can take them outside. Integral cos theta d theta, it is sine theta. So limits minus alpha by 2 to alpha by 2. So what will be this? K lambda by r sine alpha by 2 minus sine minus alpha by 2, right? Sine alpha by 2 minus sine minus alpha by 2. Sine minus alpha by 2 is minus sine alpha by 2, so it becomes plus. So you have 2 times of this. So it is 2k lambda by r sine alpha by 2. So we have our answer. This is the net field. Acts along bisector. So this is the resultant field due to arc, and this field only acts along the bisector. What we have calculated is the horizontal components, and that is the field which is present because all vertical components cancel out. This is an important step. So the resultant field of an arc is always 2k lambda by r sine alpha by 2, where alpha is the angle subtended by the arc, complete angle, and r is radius, and lambda is the charge per unit length of the charge distribution, right? Q by lambda, sorry, Q by L. L is R alpha, right? The length of the arc is R alpha. So you have to remember this equation. Uh, Try to derive this on your own again. So it helps you with the integration technique if you can do that. But remember this, how we use this formula. If it is an arc, any arc, whether positive or negative, right? There is some charge distribution. Then you should know that the field always acts along the bisector. Why? Because the vertical components cancel off. And it can be either this direction or this direction. If it is positive charges, then the field will be outward, away from the charge. And if it is negative charges, so if it is negative charges, the field will be again along the bisector, but towards the charges. So that is the difference. The direction is changing, but the magnitude will be the same value, right? Depending on the sign, you have to take the direction. And this is the field which we calculated at center. Remember this, at center, not any other point. At center, the field is of this value. Next one is the field due to a line charge. So there is a finite arrangement of charges, positive or negative. We are considering the positive charge, and it is along a line, straight line, and it is finite. It may be of certain length L. It is finite. We can extend this to infinity. First, let us see the finite case. There is a finite line charge distribution, and we want to calculate the field at a point P, which is x distance away from the line, in such a way that it subtends these angles. The angles are known here, alpha and beta. So one angle is measured from this line to the top of the line charge, and other one is measured from this axis to the bottom of the line charge. So observe, alpha is measured to top of the line charge, the tip, uh, upper tip. This is the angle due to the lower tip. So when we know these angles alpha and beta, and when we know the distance x, and when we know the line charge distributions, charge per unit length lambda, which is Q by L, then the field is given by two expressions: Ex along the horizontal line, which is perpendicular to this line charge distribution, and one along the line which is parallel to the charge distribution Ey. The field is given by two expressions, Ex and Ey, separately. If you want to calculate the net field, you can take resultant. E is root over Ex square plus Ey square. This will give you the resultant. So we are not going into the derivation. This is how the expressions are. Ex will be k lambda by d. D is the distance. Let us say d is the distance. Right. So expression is using d. So d is the distance from the point, from the line. Now it is k lambda by d sine alpha plus sine beta using these angles, and Ey will be k lambda by d cos beta minus cos alpha. So these are useful expressions, you can remember them. The derivation can be done in a simpler way. This earlier case, we have taken elemental charge and we have calculated the field and we have integrated it. So similarly, we can do the same thing here. We'll integrate the horizontal components first and then the vertical components, and we'll finally get these equations. But let us not go into derivation now. The resultant field can be given by x square Ey square root. But how do we use this? So let us take an example. Let us say there is a charge distribution of certain length L. The question is like this: finite charges, and you have to calculate field at a point. It is at a distance some x units from this. Let us say x units. So the given point can be anywhere, right? It is at a distance x. That means at a distance x, you have to take a line. The point can be anywhere. But now the point is clearly mentioned. It is somewhere here. So if you extend this line charge, you will be able to draw the distance carefully. D. So this is the line charge. We are considering a point which is at a distance d, but it can be anywhere. Now I am marking the point exactly. How do I do this? By giving angles. So I am giving these angles now. It is making 30 degrees and 60 degrees at the top and at the bottom. Now how do we use these expressions? So first of all, we have to know this lambda and d. K is the same thing. So Ex is K, lambda is, now if it is given that it has a charge Q, now Q by L will be lambda. Substituting them correctly by the distance. What is the distance? Perpendicular distance. It is small d. It is possible to give the distance accurately only if you extend this line. Right? We draw an imaginary dotted line so that we will be able to exactly see the perpendicular distance. If it is lying between the line charge distribution, somewhere here we can draw the distance easily. But because the charge distribution's region is away, the point we considered as away from the charge distribution. Now I use the dotted line to find the perpendicular distance. So anyway, k lambda by d. What is the distance here? It is given as d, so I have substituted d. Now sine alpha plus sine beta. What is alpha and beta? Remember, alpha is the angle measured from this perpendicular line that we draw and to the tip, right? So if it is upwards, we have to take it positive. Alpha is, if measured in this way, it should be taken positive. If beta is measured in anti-clockwise sense, then it is taken positive, right? If alpha is measured clockwise, it is positive, and beta is measured anti-clockwise, then it is positive, because our expression is using such conventions. Now let us take the bottom. What is the angle to the bottom? It is measured in anti-clockwise sense. Am I correct? From the perpendicular line, it is measured in anti-clockwise sense. So what is your beta here? Beta is 60 degrees. That is fine. Plus 60. Why? We have to measure beta from the horizontal line to the tip downwards in anti-clockwise sense. Here anyway we are measuring it anti-clockwise sense. So 60 degrees positive should be the value for beta. But alpha, it is different. Carefully observe. Alpha, when it is measured in clockwise sense, then it is positive. But if it is measured in anti-clockwise sense, that value must be taken as negative. See, from this horizontal line, now the tip is lying below the horizontal line. So it has caused this alpha to be measured in anti-clockwise sense. So in this case, alpha will be minus 30 degrees. Right? For our equations, in order to use our equations, alpha and beta, if they are measured in these senses, then they are considered positive. If they are measured in opposite senses, then they will be taken as negative values. So that is why, since the tip is lying below this horizontal line, now the alpha measured is anti-clockwise. So whenever you measure anti-clockwise, for alpha, it will be negative. If you measure beta, if you measure the tip, bottom tip, and if you have to measure it clockwise for beta, right, then beta will be negative. For example, let us take in this case plus plus, there is a line charge distribution, and I have taken a point below this, right, at a distance, but now it is below the line charge distribution. Now what is the perpendicular line? This is the perpendicular line. What are the angles measured? This angle and this angle from this. Now observe, the alpha is measured for the top, it is measured clockwise, so it is good. Now in this case it will be positive. But beta, check for beta, the tip is lying above the horizontal line. Now beta had to be measured in clockwise sense. There is no other way. If beta is measured anti-clockwise sense, that is the tip is lying below, then it is measured anti-clockwise sense. But since the tip is above, bottom tip, it should be measured in clockwise sense. But if it is measured clockwise, we take it as negative. So in this case, whatever is the angle here for beta, we'll take negative value of it. For example, if this is 30 degrees and this is 60 degrees, now in this case alpha will be plus 60, beta will be minus 30. Understand this. This is the convention we have used to derive this formula. So substituting these values, now it is into sine alpha plus sine beta, sine minus 30 plus sine 60, right? Similarly, you can calculate Ey. Ey will be k again lambda by d cos beta minus cos alpha. Cos beta is 60 degrees, cos 60 minus cos alpha, alpha is minus 30 degrees. So this will be the value. We will simplify, and if you want to calculate the resultant field, you can take the resultant, E equals root over Ex square plus Ey square. So this is how we use the equation. And if it is negative charge, the direction will be different. The magnitude will be the same thing, but the directions will be different. For negative charge, Ex will be pointing towards the charge because it is negative, right? Similarly, you have to change the Ey direction also. So these are useful equations. Remember them, and remember the sign convention which we are using here. So the next charge distributions are infinite line charge. Now we don't have a finite line charge. Now the line charge is extending to infinities, very long. In practice, you don't have infinite line charges possible. This scenario is an approximation. For example, if you want to consider the field which is close to a finite charge, let us see that we have a line charge distribution, and we want to calculate the field at a particular distance, but which is very close to the line charge. That means somewhere really close. Now for such a point which is very close to the line charge, even though this is finite, the angles alpha and beta are very large and the distance is very small, and for such a point it seems like the line charge is extending to infinity, right? So in practice, in these kind of situations, the finite charge seems to be infinite, right? For example, we have an idea about this board, right? For this observer who is at a particular distance, let us say the marker is observer, and he will be able to see this finite. The board seems to be finite for him. The angle subtended is roughly 60 degrees or 70 degrees. But if this observer is going very close to the board and he is now observing the board, right? So very close and observing the board seems to be infinite. When you take the points very close, the system seems to be infinite, it subtends large angles. So in such cases, we have an idea of infinite line charge. Practically, infinite line charge is not possible. You cannot create a line charge distribution extending to infinity all over the universe. It is not possible. But in practice, for these kind of scenarios, we can go by this method, right? So in such cases, the tip of the line charge distribution, the upper tip is extending to infinity. So the angle alpha will be roughly 90 degrees. It is extending to infinity. It has become perpendicular. If the tip was here, it is measuring some angle. The angle is increasing as it goes higher and higher, and it becomes 90 degrees if it goes to infinity. Similarly, bottom angle also, beta is measured at an angle, but if it is extending, beta gets bigger, and if it goes to infinity, the beta becomes 90 degrees as well. So this is what happens. The angles seems to be very large, and the line charges seem to be infinite. So in this case, Ex and Ey, let us calculate the field. So it is k lambda by d into Ex is sine alpha plus sine beta. Sine 90 plus cos 90, that is 1. Sine 90 is 1, cos 90 is 0. So you have k lambda by d. And what is Ey? Ey is k lambda by d into cos beta minus cos alpha, right? So cos beta is 0 degrees minus cos alpha, that is also 0 degrees. Sorry, 0. Cos 90 is 0. So we have 0 for Ey. There will be no vertical component. The field will be only acting along horizontal. So if you take a point very close to a finite charge, you should know that there is only Ex at that point. That means the field is uh, only directed along this perpendicular direction. Let us say this is the marker. When you take a point very close to the marker, the field is coming out perpendicularly. At such close points, Ey is not possible, because for such a close point, on either sides we have equal charges, and the vertical components get cancelled out, right? Field due to this will be directed downwards, and field due to this system will be directed upwards, and they will cancel out. But the horizontal components, they will add up. That is why we are getting this. Anyway, I want you to remember this. So the resultant field will be, E net will be k lambda by d, or you can write it as lambda by k is 4 pi 1 by 4 pi epsilon naught d. So this is the field at a point which is at a distance d away from an infinite line charge, or it is the same thing for a finite line charge when the point is very close. That means d is very small in comparison with L. In this case, even the finite situation becomes infinite. So even in this case, when it is very small, you can write the field as lambda by 4 pi epsilon naught d. Okay, the next one, field on axis of a ring of charge. So we have a distribution, charge distribution, linear charge distribution. Here also it is a line, but now it is a complete ring. We want to calculate the field along the axis at any point, which is d distance away from the ring. From the center, we are calculating the distance, right? We have a ring here. From the center of the ring, we are calculating the perpendicular distance, and on the axis, we want to calculate the field. So on the axis, the field always acts along the axis. This is due to symmetry as well, because you pick 2 points up and below, right? Field due to this and field due to this. The ring, imagine the ring here. So field due to the topmost charge and field due to the bottommost charge, they will be in such a way that their vertical components again cancel out. So if you take two lines, these two vectors, they have their vertical components being cancelled out, and only horizontal components add up. So anywhere if you take diametrically opposite ends, right? Take the diameter of the ring and consider two elemental charges on either sides of the diameter. Now fields due to them, their vertical components will get cancelled out, only horizontal components add up. That is why the net field acts along axis. If it is plus, it will be away. If it is minus negative charge, it will be towards the ring. That is the difference. Direction will be different, but the magnitude is the same thing. So the magnitude, the field magnitude in such a case is given by this expression. So this can be also derived using integration technique. But let's not go into that. Here, Q is the total charge on the ring. Small d is the distance from center to that location. Capital R is the radius of the ring. So it is K capital Q d by d square plus r square whole power 3 by 2. Right? So remember these equations, they are useful. So there are other charge distributions also, like hollow spheres and solid spheres. We will discuss about their fields after the topic Gauss law. After one or two lectures, we will be discussing about Gauss law, and then we will discuss about the fields of other charge distributions. So the next topic now, let us go and continue with electrostatic potential energy. Electrostatic potential energy. This is very important topic. You should have a clear understanding about what potential energy is. The conservation of energy is a very important topic when it comes to examinations. You will be asked questions about conservation of energy in different systems. In the case of mechanics, in the case of electrostatics, or in any other case, we will be asked about conservations very often. So, in order to do those problems easily, you should understand what these energies actually are. So, the potential energy, electrostatic potential energy, is a very important topic. Let me start with the definition of this. So, for any system, if we have to understand what potential energy is, the first thing is this: the potential energy exists only in the case of conservative systems. Potential energy exists for systems with conservative forces. So, this is very important. Whenever you are discussing about potential energy, you should understand that this potential energy is arising in a system only in relation to the conservative force that is present, right? So, not all forces can be related with potential energy. Only conservative forces are capable to create this idea of potential energy, right? So, conservative forces. What are conservative forces? The work done by such forces will be path independent, right? Conservative forces are those by which uh, the work done is path independent. So this is the clear difference between conservative and non-conservative forces. If the work done by any force, if you observe it to be path independent, that means whatever the path may be, say the particle is taken in a particular way, we are doing some work on it, right? So in whichever way you take, whether you take it in a curved line or a straight line or in any other path, if the work done is coming out to be same, then you should know that it is a conservative force. Right? Take the example of gravity. So in work per energy chapter, you might have studied this. If you take a point mass very close to Earth, this is happening very close to Earth. Now if you increase the height of the particle, right, by a small distance h. Now as long as height is very small in comparison to radius of earth, we can take an approximation. We can use the force to be mg. The force acting on it is mg, the weight. But if it is higher and higher, then gravitational effects come into picture. We will be using gm by r square into m, right, by the help of gravitational equations. But as long as these heights are small, when it is happening very close to Earth, g will be constant, small g. So we can straight away take the force to be mg. So if you have taken this object to a certain height, small h, now what is the work done here, right? It is mgh to increase the potential energy. You know that the system's potential energy has increased. In whichever way you take, the work done by the gravitational force will be the same thing. What is the gravitational force here? Mg downwards. Work done by gravity. It is mg, force into displacement. Since this is a constant force, force into displacement, but displacement is in opposite direction. Force is downwards, displacement is positive, so it is minus mgh. So work done by the conservative force, which is the gravitational force in this case, is minus mgh in whichever path you may take the object. It is the same thing. So this gravitational force is a conservative force. So we know that there is a term potential energy associated with this conservative force. Only in the case of conservative forces, this concept of potential energy comes. So the potential energy, how is it defined now? The change in potential energy is always the negative of work done by conservative force. This is the definition. For any system, the potential energy is defined in this way, right? So definition: change in potential energy is the negative value of work done by conservative force. So it can be only related with a conservative force, and in a system, if you have make some changes, we have to calculate the work done by conservative force and the potential energy change. The change in potential energy will be negative value of the work done by the conservative. That means delta P, change in potential energy, will be negative of work done by conservative force, or it is P final minus P initial is equal to minus Wc. This is the basic idea. Or if you want to write it in a differentials, du will be minus dwc. Right? The small increase in potential energy, small change in potential energy is equal to negative of small work done by conservative force. This is how it is defined. We do not have definition for potential energy. We only have definition for change in potential energy of a system, right? So we only know by how much the potential energy of a system is changing, but we cannot know for sure what potential energy of a system is. We can find the potential energy by taking references. We can say that the potential energy in this case is mgh, but actually the potential energy change is mgh, right? And now the reference in this case, we have chosen that the potential energy on the ground is 0, right? So that is our reference. So if the potential energy on the ground is 0, the final potential energy is mgh and initial potential energy is 0. So that is the negative of work done by conservative force. This is the exact relation what is present there. The negative of the work done by conservative force is minus mgh, and negative of that is mgh. So by definition, what it is, this is equal to change in potential energy, U final minus U initial. But because we take that this is reference, the surface level, and we consider it to be zero, now we say that the object, when it is present here, it is having potential energy mgh. But it is because only we have taken this as a reference, right? So in such cases, we can say the potential energy of system is some value. But by definition, we only have always the change in potential energy in a configuration. There is a certain configuration. It can be arrangement of masses. It can be arrangement of charges. But you do some changes, there is some change in potential energy occurring, right? That is defined this way. It is always equal to negative of work done by conservative force. So by making use of this definition, let us find what electrostatic potential energy is. Let us discuss the potential energy of two charge system. 2 point charges. So we have a system of charges, 2 point charges Q1, Q2 at a certain separation. Now let us fix this charge and let us move only Q2 with the help of some external agent. Uh, See, in this case, if these two are positive charges, what happens? If this is fixed, because they are positive charges, they will repel, and this will be pushed to infinity. This will accelerate, the charge will go to infinity, right? But we don't want that to happen. We have an external agent who is controlling all this. We're carefully taking the point charge from one location to another location. Someone is holding the charge and slowly taking it to the other position. So initially, let us say it is at a distance Ri initially, and finally it was taken to some position R final. Right? Let us say this is origin as well, O, and let us say this is x-axis. So we should fix the system into certain mathematical criteria so that we have equations, proper equations. So I am considering the line joining these two charges to be x-axis. One of them is at origin. Now other one is freely moving along x-axis. The initial distance is Ri, final distance is Rf. Now in this situation, I want to calculate the change in potential energy. So when the system is Ri apart, it has a certain potential energy. When it is far away, it might have a different potential energy. The potential energy might change. The electrostatic force is also a conservative force. So here we have potential energy related with the system. Because this potential energy depends on configuration of the system. Configuration means how the system is arranged, what are the separations, what is the orientation, etc. So if you have changed the configuration, initially they are some distance apart, now they are another distance apart, far away. So it's possible that there is a change in potential energy. Now let us calculate this potential energy. Let us estimate this. So as this charge is being taken away, let us consider an instant where it is moving, and let that instant be this, when it is at a distance r. Okay. So all distances are measured from origin. We are moving it at a particular distance r. The initial is Ri, final is Rf. Some intermediate position R. Let us say it has moved to a further distance dr. Right? Now, what is the work done by the conservative force? With the work done by the conservative force, we can find potential energy. See, du is minus dwc, negative of the work done by the conservative force. So let us find work done by conservative force in moving a small distance dr. Right? The work done is force into displacement. Force between these two, when they are r distance away, is kqq by r square. So it is k q1 q2 by the distance, present distance is r square. At that instant, the force is k q1 q2 by that distance r square, acting along the line. If they are positive charges, let us say for now they are positive charges, the force is directed forward on this particle, it is being pushed. So force into displacement is dr, positive, right? So dot product gives you a positive value, both are in same direction, angle is 0, f bar dot ds bar, right? Force is along x-axis and displacement is also along x-axis. So we have angle between them 0 degrees. So simply we can multiply force and displacement dr. So this is the work done by the conservative force. What's the potential energy? Negative of this. Anyway, let us calculate the work when it is taken from initial to final points, right? The total work. So the total work will be to take it from initial point to final point by conservative force. See, I am always using the subscript c here. We have to calculate the work done by conservative force, not any other one. There may be external agents also doing some work, but that is not our interest. Work done by conservative force is k q1 q2 by r square dr integral from r initial to r final. So this is k q1 q2 is taken outside, 1 by r square integral is minus 1 by r from r initial to r final. If you substitute k q1 q2 into minus 1 by rf minus 1 by ri, right? So this is k q1 q2 into 1 by ri minus 1 by rf. So this is the work done by conservative force in taking it from initial to final position. So now tell me, what is the potential energy? Delta P. What is the total change in potential energy? U final minus U initial, right? So that is U final minus U initial is equal to negative of the work done, which is k q1 q2 minus 1 by ri minus 1 by rf. So let's write it here. Finally, we have u final minus u initial equals k q1 q2 minus of this 1 by rf minus 1 by ri, right? Rf is the final separation, ri is the initial separation, and u final minus u initial is the change in potential energy. So this is how we define potential energy of the system, the change. But normally we use potential energy terms like mgh, minus gmm by r, etc. So how do we do this? By taking a reference. So in all cases, generally, reference is considered at infinity. infinity. So if Ri is infinity, Ui is taken to be 0. This is the reference. We define potential energies of the system generally by taking this convention, this reference, that whenever the potential energy of the system is calculated at infinity, it is considered to be 0. This is a reference value. So when they are initially far away, right, is this Ri, initially they are not here, they are far away, Ri is infinity, so this term reduces like this. U final will be the final potential energy when they are separated by a distance r. Let us say initially they are at infinity and now they are separated at a distance r, right? Initial case is infinity, final case is at a separation r. Now substitute u final, that means u at the configuration when the distance is smaller, minus u initial, initial cases when the separation is infinity, is equal to k q1 q2 1 by rf. Rf is final r, infinity is ri. So this becomes, since u infinity is taken to be 0, initial value u at infinity is 0, now u potential energy in such a configuration is k q1 q2 by r. So observe this very carefully. This is very important. By taking a proper reference, that is the reference is our infinity. When they are separated very far away, we take the potential energy of the system to be 0. That is the reference value, standard. So by comparing that, the present potential energy when they are separated by distance r is ur here. The subscript r implies that we are calculating the potential energy when they are separated by r distance. So ur minus this is chosen to be 0, right? So this becomes 0, and k q1 q2, and the final distance is r, initial distance is infinity. So we will be left with k q1 q2 by r. So this is how we get the potential energy of the two charge system when they are separated by a distance, any distance small r, right? Two charges, distance between them is small r. The potential energy of this system is k q1 q2 by r. Very important result. We often use it. And q1 q2 can be positive charges or negative charges, or plus or minus or plus. So in this equation we will substitute with the charge sign. So if one is positive, other is negative, we will have negative value for the potential energy. If both are positive, we have positive value for potential energy. Even if both are negative, we have positive value for potential energy. So this is one important result. We'll discuss further in the next class.